Well, since we moved over here, I didn't notice any jackhammering going on in Wixon Hall this morning.
As soon as we move back
But temperature here seems to be pretty good. I think we'll just stay here. Besides, it's a larger room. You're not so crowded. Well, we talked about iron last time. Today we'll devote the lecture time to copper. And copper really presents more of a problem than iron as far as clouding is concerned, because such a small amount of copper can cause clouding. Where we're generally talking with iron 8, 10, 15, 20 parts per million to cause clouding, there are well-documented cases where 1/10 of a part per million of copper has caused clouding. Though ordinarily the winemaker is not concerned with 1 or 2/10 parts per million of copper, some of them will even tolerate up to 5/10 of a part. But we feel that anything over 1 or 2/10 parts per million of copper is getting into the possibility of having trouble. Well, if you look at the lecture outline that's handed out last time, page 3 of it, the characteristics of copper casts, you can see that the cation involved, of course, is copper, and the anion involved is sulfur. And a compound that's formed is either cupric sulfide or cuprous sulfide. Initial appearance is a white haze, and the final is a reddish-brown deposit. If you expose it to air after the copper sulfide is formed, it may or may not disappear. And I'll go into that in some detail later on to explain why it may or may not disappear. On exclusion of air, it appears. In other words, it requires reducing conditions for the copper sulfide cloud to form. It appears in light, and in darkness it may or may not disappear. And as far as temperature is concerned, most chances of it forming at higher temperatures. If you add peroxide, it may or may not disappear. And again, I'll go into the reasons for that a bit later. And pH does affect, though not as drastically as it does in the case of the iron or ferric phosphate cloud, where it only formed in the range of 2.9 to 3.6 pH. That's not true here, but pH does have a measurable effect upon the formation of the copper sulfide cloud. Now, Table 5 gives a postulated mechanism of copper cast. I say postulated because it's not completely accepted this is the route of formation of the copper cloud. That there are many other factors involved and other ways for the copper cloud to form besides this one which is postulated. And that's the cupric copper is reduced by reducing substances in the wine to cuprous. Then the cuprous reacts with the sulfur dioxide, in this case the sulfurous acid, which would be there in a water solution or alcohol water solution. And the copper is again oxidized to the cupric form, and hydrogen sulfide is formed. Then the hydrogen sulfide reacts with the oxidized copper to form cupric sulfide. And the cupric sulfide will flocculate, provide the electrolytes and colloids present, and you get haze, turbidity, and deposit. And disappearance would be caused, according to this postulate, by introducing air or peroxide. Because in order for the copper sulfide cloud to form, you must have reducing conditions present in the wine. That's the only way you get the hydrogen sulfide to react with the copper. Now, the factors affecting. You must have reducing conditions. Number one, you must have reducing conditions. And that's why a nominal copper pickup prior to fermentation, for example, in using crutches that contain brass or copper or pumps, doesn't pose too much of a problem because the major part of the fermentation, reducing conditions prevail, and the copper will drop out as copper sulfide. So if you rack that off before you expose the fermented wine to air, you've gotten rid of most of the copper that you've picked up. So reducing conditions must prevail for the copper sulfide to form. So, like is true of the iron cloud, the ferric phosphate cloud formation, the redox potential is very important. In the case of the iron cloud, we wanted a high redox potential, in other words, a high potential for oxidative conditions, because we wanted to oxidize the iron to the ferric state so they could react with the phosphate to form the ferric phosphate cloud. Here we want a low redox potential if we're going to have a copper cloud formation to reduce the copper and then form the copper sulfide. In addition to that, of course, in addition to the factors affecting the redox or reducing conditions, there are also the factors that affect flocculation. So let's take these up in turn. Redox potential factors. Naturally, aeration will inhibit the formation of the copper sulfide or prevent it altogether because we must have reducing conditions. The presence of iron and rise in temperature also inhibit the formation because iron and a rise in temperature will raise the redox potential. So that'll inhibit the formation of copper cas. Aeration, iron, and a rise in temperature all inhibit the formation. But there's another way of looking at it. Because of the fact that iron and heat have an increase in the oxidation rate, and thus removing all of the oxygen that's present if you have a closed system, then they can hasten the occurrence of the copper sulfide because they'll hasten the achievement of the reducing conditions that are necessary for formation. So initially the effect is to inhibit, and after the removal of all the oxygen, the long-term effect is to promote the formation of copper sulfide. As we go through the quarter, you'll find that there are a lot of contradictory factors, actions, such as the one I've just described. Light, sulfur dioxide, and ascorbic acid all will favor the formation of copper sulfide. Light, sulfur dioxide, ascorbic acid, because they all lower the redox potential. So light, sulfur dioxide, ascorbic acid favor the copper sulfide formation. Now at table 5, showing the possible reactions that occur in the formation of the copper sulfide, the primary reactions that are given are naturally copper and sulfur. But the formation of copper cloud, so-called copper cloud in wine, is not that simple. In fact, it's much more complicated. A number of years ago, one of the PhD candidates in agricultural chemistry chose as his dissertation problem to try and determine the reasons why there is a wide variation among wines in their susceptibility or their resistance to copper clouding. Up until that time, it is widely noted that there could be a very, very large difference between two wines supposedly of about the same composition in their susceptibility to copper clouding, and no one knew the reason for it. Well, in a beautiful piece of work over a period of some 3 years, he came up with the answers. And since that time, it's no longer a mystery. We understand why, and it's really helped in controlling the problem. Look at table 6 on page 3. Types of copper cas. In case number 1, the substances that are present are tannin, copper, and sulfur dioxide. Now this is all work with model solutions, so they absolutely knew what the constituents were. With tannin, copper, and sulfur dioxide, no cloud formed. Anyone know why? Well, it's very simple. You don't get a visible cloud formation in the absence of protein. Protein is essential if you're going to have a visible cloud formation. Case number 2, you have all 4 possible reactants there: protein, tannin, copper, and sulfur dioxide. You get very fast cloud formation, which may be partially reversed. Now the reason you got very fast cloud formation because the copper sulfide that formed was quickly flocculated by the protein. In other words, you had to have the protein reacting with the copper sulfide, to get a visible cloud formation. And it's partially reversible, but growing less so with time. In the third case, where you have protein, tannin, and copper, you get slower cloud formation. And this cloud may be partially reversed. Well, this is a copper protein cloud. You have no sulfur dioxide present. You have protein, tannin, and copper. So you get a copper protein cloud, and it forms more slowly than a copper sulfide. And it's partially reversible, but growing less reversible with time. The fourth case, you have only protein and tannin. You have no copper, no sulfide, no SO2, and you get a protein tannin cloud, which forms very slowly compared with the others. And it's completely irreversible. Any cloud that you form remains. And what we had been calling copper cloud for many, many years was actually 4 different types of clouds. And protein tannin was included in that because it was mistakenly thought to be a copper clouding rather than a protein tannin cloud. Any questions on this?
What's the fourth class?
Fourth class?
You said there were four types of clouding.
The 4 types of clouds, actually they are copper sulfide, copper protein, and tannin protein. There are only 3 different reactants or combinations of them, but the constituents that are present will affect the rate of formation and the degree of irreversibility that occurs. Any other question on this?
Yes, in case 3, if ferric ion is present.
Pardon?
In case number 3,
Yes?
if a ferric ion is present, does that inhibit cloud formation?
Ferric iron? Yes. It would, because if you're talking about a copper sulfide cloud, it certainly would. If you're talking about a copper protein cloud, no. And of course, a protein tannin cloud, no effect.
If you had no protein at all, then ideally you wouldn't have to worry about copper or iron.
That's right. I'll go into that in some detail later
Why
on.
don't we skip metals and concentrate on protein?
Well, we must build this up. We must establish a firm foundation, metallic foundation, before we go into these organic things. Any other questions? Well, I think we can conclude from this that we can form copper sulfide without any visible change in appearance. You've got to have protein present for its flocculating effect if you're going to have a visible change in appearance. Now, if you only have copper sulfide there, and it's not attached to the protein, then by introducing air or peroxide, you can cause its breakup. Or if there is a small visible cloud, it can be completely reversed by the addition of peroxide or vigorous aeration, because you'll oxidize the copper sulfide to copper sulfate. But if you have any appreciable interaction of copper with a protein, then the interaction will initiate denaturation of the protein. And the degree of denaturation will determine the degree of irreversibility of the cloud formation. If the protein is appreciably denatured, then if you are to introduce peroxide or aeration and start oxidizing the copper sulfide to copper sulfate, if the protein has been appreciably denatured and the copper has had a chance to react to some of the reactive sites, then you're not going to get the complete reversal of the cloud. And the degree of reversibility of the cloud is going to depend upon the degree of denaturation of the protein. And that's why immediately after the start of the reaction, your cloud is completely reversible or almost so, and with time it becomes less and less reversible because you are denaturing the protein more and more and more. Opening up the reactive sites, allowing the copper to react with the reactive sites of the protein.
This denaturation then continues over a period of time.
Right. It's a time reaction. Now the copper protein cloud, of course, is less reversible than the copper sulfide cloud because of the fact that the copper is more firmly held by the protein. And the protein tannin cloud is completely irreversible. Because you've had an interaction there, you've had a denaturation and a firm chemical interaction between the tannin and the protein, and there's no way that you can break that up like you could by oxidizing the copper sulfide to copper sulfate. This all clear? Good. Took me a long time to get it clear in my own mind. Now I want to talk something about the complexing factors. Remember I'm talking about the ferric phosphate cloud, that some of the organic acids had a side effect, alcohol, pH, tannic acid, and of course the oxidation state factors. They all apply here on the copper clouding too, but not to the same extent. For example, as you recall that in the presence of 6 4/10 parts per million of iron, that citric acid at a certain pH would complex 100% of the iron that is present. Well, we'll take 6 4/10 parts per million of copper, and we'll use 0.01 molar amounts of the various acids. Where citric complexed 100% of the iron, it complexes 28% of the copper. Malic, 8%, tartaric, 5, and succinic and lactic, 0. So you see that the organic acids have very little complexing power over copper compared to what they have over iron. But in the case of citric, enough that it's appreciable, and in borderline cases can mean the difference between a cloud and no cloud. And of course, like again with the iron clouding, the effect of the pH is to increase the complexing with increasing pH. Increasing pH increases the complexing power. For example, with citric again, at pH 357, 0 was complexed. And at 425, 28% was complexed. And again, that effect is due to the fact that at the higher pHs, more of the acid is dissociated. And it's a dissociated form of the acid that has the complexing power. If you increase the alcohol concentration, it'll have a small favorable effect on preventing copper cloud formation, because it'll increase to a small percent the amount of the copper that is complexed by these complexing acids. And tannic acid slightly increase the complexing power of malic and tartaric acids. So if you have a fairly large amount of tannic or tannin present, then you'll slightly increase the complexing power of the malic and the tartaric acids. I think this is all rather clear-cut and forthright. Now I want to go into the flocculation and precipitation factors. These are colloids, clarification, filtration, temperature, and pH. I said you had to have proteins present for a visible cloud to appear, in other words, to achieve flocculation, and of course the proteins must be colloidal, which they are naturally. So colloidal proteins are necessary for flocculation to occur, for a visible cloud to be formed. But you can also have protective colloids, which inhibit flocculation and will prevent the formation of a visible cloud or a deposit. So you can have two types of colloids present, those which inhibit flocculation or may prevent it entirely, those which aid flocculation and can achieve complete flocculation if all conditions are favorable. So you must think of colloids in two ways, as either favoring cloud formation or hindering cloud formation, according to whether they are not protective colloids or they are protective colloids. And the way I try to present the concept of a protective colloid, I have no physical basis for or scientific basis for describing it this way, but it's an easy way of doing it. And that's just think of the substance that you want to flocculate. If you have protective colloids present, forming a skin or an envelope around the substance and just preventing its action. I say I have no scientific basis for this, but that's the way I like to present it because it's easy to visualize it.
They just form a skin around there to prevent that from dropping it.
I have the slightest idea how they do it.
Well, the way you're presenting it,
That's the way I present
your
it.
theory is.
It forms an envelope or skin around the substance and prevents it from being available for reaction. Yes?
Are protective colloids presumably non-protein?
Not what?
Are they presumably non-protein, or are they
No, they're protein. They can be proteinaceous, right. Because one of the ways of forming protective colloids is to heat wines and change some of the protein from a flocculating type of protein into a protective colloid type of protein. There are other protective colloids also, gums, dextrins, and so on, can all act as protective colloids. If anyone has a better explanation of this action, I'd surely like to hear it. Now, what would be the effect of clarification? Well, if we clarify wines, and I'm thinking now particularly of white wines, if we clarify them with bentonite, which is our most effective fine agent for the removal of protein, then we can knock the protein content down to the point where we would not have a visible copper cloud formation because there would not be enough protein there to achieve flocculation. So fine with bentonite, removal of proteins is a positive step towards ensuring that our wines will not suffer our copper casting.
What does it do to the taste?
Pardon?
What does it do to the taste of wine?
Can't hear you.
What does it do to the taste of wine?
Bentonite finding? Nothing? If it's done right? So that's one of the reasons why we clarify the bentonite, particularly on whites. Yes?
Sort of off the subject, but you said if you do it right, what's the maximum time we can leave bentonite connected to the wine?
The maximum time?
Yeah, without harming the sensory.
Oh, anywhere from a week up.
You could, in other words, you could just leave it.
Yeah.
Stick with the wine forever and nothing would happen.
With an average sized tank, it takes almost a week for the bentonite to fall down at the bottom of the tank. But the main thing in using bentonite is the way it's prepared, the way it's introduced, and to avoid introducing a lot of air.
So there's a minimum amount of time
It'll vary entirely with the deposit that's formed, the pH of the wine, the condition of the wine, the size of the tank. So many factors.
Where can you find out that information?
Well, the best rule of thumb I know is to get off the bentonite lead as quickly as possible.
Get it off the leaves as quickly as possible?
Right.
What if you get it off too quick and it all hasn't settled?
You'll soon find out. You won't be able to filter it. I don't know any that plugs the filter faster than bentonite leaves. No, the winemaker knows by experience with the types of wines he's working with, the size of the tanks, and the temperature of the wine and so on, how long it's going to take for the bentonite to fall through the wine and for the wine to be bright. And if he doesn't know, it's possible to follow it just by lowering a thief into the wine at various levels and pulling out a sample. It's that simple. Filtration can also have an effect. Filtration can favor copper clotting or it can hinder copper clotting. It can hinder copper clotting if, as a result of filtration, we will remove suspended particles of protein that have not fallen out of the wine, but have become large enough under refrigeration to be removable by filtration. We can favor the chance of copper clotting by filtration if the filtration will remove protective colloids. These protective colloids have prevented the reactions that we are subjecting the wine to try and achieve the stability that we want. And if we remove them, then a wine which has formerly been stable by the usual test will suddenly become unstable. So filtration can have both positive and negative results, depending upon the condition of the wine and the substances that are present in it.
How did you say it could hinder?
It could hinder the formation of copper clotting by removing proteinaceous material, or it can promote the formation by removing clotting material. And lowering the temperature will promote the formation of the copper cloud because it'll increase flocculation, because lowering the temperature decreases the effective protective colloids. As we lower the temperature, we lessen the effective protective colloids, and therefore it's going to be an aid to the formation of a visible cloud.
The temperature.
It decreases the effective protective colloids. Lowering the temperature decreases the effect of protective colloids.
How does this occur?
The skin isn't full.
It just.
You ever put your hand in cold water, notice how the skin shrivels up? Same thing. At least that's my explanation. You can have your own if you don't like that one. Any other questions? Now I want to go into a very interesting phase of this problem of copper clouding, and that's the variability that I mentioned earlier in the power, the susceptibility, or the resistance, whatever term you want to use, of wines to copper clouding. And as I also mentioned earlier, Keene's work has thoroughly explained this. He showed that the complexing power of the wine and the kind and the amount of the proteins that are present were the main responsible factors, and especially the latter, the kind and amount of the proteins that are present. Now, why was the kind of protein important? Well, those proteins that contain a high percentage of dithiol compounds, the sulfur-sulfur linkage, are most susceptible to the attack of copper and a number of other things because it will break the sulfur-sulfur linkage and the copper will attach on to one of the sulfurs. So those proteins that are rich in sulfur amino acids, since naturally proteins are made up of polypeptides, which in turn are made up of amino acids, will more easily precipitate copper from wine than wines containing proteins that are much less rich, contain a much lesser proportion of the dithiol or sulfur-bearing amino acids. Sulfur dioxide, ascorbic acid, or light, or all three, have a decided effect upon this reaction. Because of their effect upon the sulfur-sulfur linkage. So you have to have reducing substances, SO2, ascorbic acid, light, and light is about the most powerful of them all. If you're going to promote a copper reaction with one of the sulfurs of the disulfide linkage, because you must break this linkage before the copper can react, and these are the things that are responsible for breaking it. Now, if you have sulfhydryl, almost got it right. groups, in other words, the SH group, then you don't need these reducing substances because naturally you only have this SH and the copper can react directly there with the sulfur. So that's the reason why the type of protein or that the makeup of the protein is of quite a bit of importance in the susceptibility of wines to copper clouding. Because if you have the dithiol linkage, they're going to be more resistant because you have to break this linkage first and put a hydrogen on breaking it. And you need SO2, ascorbic acid, or light, which are the main things that are responsible for breaking this linkage, or some other things also, but these are the main three. You must have those present to break the linkage to get the reaction going. Whereas if you just have the sulfhydryl grouping present, your copper can react with it directly. Now on page 4, table 7, some more of Keen's work. He used white table wines with 250 parts per million of sulfur dioxide and 6 parts per million of copper. Now that's a tremendous amount of copper, and it's a very good dosage of sulfur dioxide for that matter. In other words, he wanted to set up the wines so that you would almost guarantee that he's going to get a copper cloud formation. If you look over the left-hand column under the before bentonite, you'll see the protein content in parts per million of these wines. And you look at 113 degrees Fahrenheit, the wines were stored in stoppered glass bottles in the dark at 113 degrees Fahrenheit. And these protein contents ranged from 19 to 81. They became very cloudy after 24 hours in the dark at 113 degrees Fahrenheit. Whereas the two wines containing 6 and 7 parts per million of protein were perfectly clear after 5 months under those conditions. So you can see that the amount of protein is very important. Then he took aliquots of these same wines, which of course had not been treated, and removed protein by bentonite fining. And you can see at the next column there gives the amount of protein in the wines after the fining. Again, these were stored at 113 degrees Fahrenheit in the dark, and they're all okay after 5 weeks. So that was a double proof that the removal of the protein, or the naturally low protein contents of the wines, were the best insurance you had against the possibility of a copper cloud formation. If you got the protein content down low enough, then you don't have to worry about a copper cloud formation. But 6 parts per million of copper is a horrendous amount. Yes?
Do you know what bentonite figures he used?
How much he used? Well, I think he standardly applied 10 pounds per 1,000 gallons and then analyzed for copper, or for protein. It's been a long time ago and I've forgotten the exact detail. To see me, that was his standard dosage. It was 10 pounds per 1,000 or 1,200 milligrams per liter. Now he took another aliquot of these same wines that had been bentonited and stored them in sunlight in 3 different colored bottles: white, green, and brown. And compare what happened in the white bottles stored in sunlight. Very cloudy after 2 hours, as compared with okay after 5 weeks at 113 degrees Fahrenheit in the dark. And so on down the line there. The green, about the same result as with the white. Now look over under the brown heading there. This wine, which became very cloudy after 2 hours in a white bottle in sunlight, was okay after 3 days in the sunlight in a brown bottle. And you can see that this brown bottle greatly increased the resistance to copper cloud formation as compared with wines that are stored in white or green glass. Now, I think you all know the reason for that. It's the particular rays of the spectrum that are either passed through the glass or screened out. Brown glass absorbs above 500 nanometers, green 400, and white below 350. So it's the UV spectrum that is the one that's really the reason the spectrum is responsible for the action. It's all clear?
Well, if the brown only absorbs above 500 and the green absorbs above 400, isn't the green effectively blocking out?
I'm sorry. Transmits instead of absorbs. I just give myself completely about 180-degree angle every once in a while. This is one of those times. That should suit everybody, better including me. Now, the sulfur dioxide, remember there was 250 parts per million of sulfur dioxide present, also present in the dark. And sulfur dioxide can denature proteins in the dark, but the reaction rate is so slow that these wines were stable after, 5 weeks in the case of some of these wines, after storage for, 5 months after storage at 113 degrees Fahrenheit. But if you have sulfur dioxide in the wine and you put it out in the sunlight, you can almost see it change in front of your eyes if you store it in white bottles in the sunlight. And the reason for that is because the sunlight it causes a photochemical decomposition of the protein. In other words, you might say it ruptures the proteins, exposes the reactive sites, and causes the rupture of the disulfide bond. So sunlight is about the worst enemy there is to wine. And if you want evidence of that, go to some liquor stores that have the habit of putting an exhibit of bottled wines in the window, especially if they're light green or white. If they've been there for any length of time, you can sure see what sunlight does to wine. Any questions on this?
What about artificial light?
It's a UV portion that's bad. So ultraviolet light would be beautiful for promoting these reactions. When you look at Table 8, there's a summary there of the various factors, their effect on the formation of copper complex, of copper sulfide, and the flocculation and precipitation. I think that table is self-explanatory. And the recommendations, you can read those because they're self-explanatory. That'll leave me 5 minutes to discuss the removal of copper and iron from wines.
I worry about it.
I still run into it occasionally, even in this enlightened age.
Say what?
I still run into copper clouding and very occasionally iron clouding, even in this enlightened age, this age of stainless steel and glass and various synthetics. Besides which, sometimes you get a wine that's very susceptible to oxidation or to other undesirable actions. And quite often, the wine can be made much more resistant by reducing the metal content to the lowest possible level. The method of removing heavy metals from wine that has been in use for very many years, developed originally in Germany, called the Mossender process, or blue fining, is the use of potassium ferrocyanide. Potassium ferrocyanide. In fact, it's the only truly satisfactory method that we have, is to use potassium ferrocyanide to remove copper or iron.
Legal?
Pardon?
Legal?
It's legal in Germany. It's not legal in the United States. It's legal in some other countries also. Not in France, though it's widely used there. Now, there are a number of other methods that have been developed and tried as a substitute for potassium ferrocyanide because of the fact that there aren't too many countries where potassium ferrocyanide use is legal. And there's always the fear that some cyanide residue may remain in the wine. Of course, subjecting a person to a very big dosage of cyanide fumes is one of the methods that's formerly used in this state for executing criminals. Though I must say that it's effective, but it's inefficient. In that the human body can handle relatively large amounts of cyanide because it can very quickly react with the cyanide and detoxify it. So, unless it's a very gross misfinding with potassium ferrocyanide, there wouldn't be the slightest danger in the world from drinking a bottle of wine containing some cyanide residue, because the amount that's there would be so small that the system would have no trouble whatsoever in handling them. Well, one of the methods used is aeration followed by refrigeration. The idea being, in the case of iron, to get it into ferric form, the ferric phosphate would form, and then you refrigerate it, hopefully get the particles to coalesce to the point large enough to be removed by filtration. In the case of copper, exactly the opposite. You would add SO2 and then heat to attain reducing conditions, form the copper sulfide, and hopefully remove it by filtration. Well, both of these methods would only remove part of the metal, and the amount that is removed is very unpredictable, and of course they're undesirable, especially the heating, undesirable from the standpoint of the danger or the damage it did to the quality of the wine. Phytates, the naturally occurring compounds in some plants, have been used for removing iron, but again they only remove the ferric iron, phytates. So you have to oxidize your wine to get as much iron as possible into the ferric form before the phytate will react to precipitate it as the ferric phytates.
When you say aerate, how is this done? Is this done by stirring or usually, or?
By bubbling air through the wine.
Bubbling
In other words, agitating the wine with a stream of compressed air. Not recommended.
Is that a large amount of air? As much as they can put into it? They only do this in red wines, right?
They don't do it at all. There are several chelating agents. Fluorescein, which is ethylene diamine tetraacetate, if you want the chemical name for it. But just think it was fluorescein, that's much simpler. It chelates iron very well, and it does a pretty good job with copper. In other words, it's a chelating agent. It just ties it up so tightly that it can't react to form the clouds. However, it remains in the wine, so it poses both a problem with the FDA, the Federal Food and Drug Administration, and also with the BATF, the Bureau of Alcohol and Tobacco and Firearms, because it's never been approved for use in wine. And there's always a possibility that for permission to use might carry the stipulation that would have to appear on the label. Of course, that's something the wine industry doesn't want to do, is to say, this wine has been treated with versene and it'll be found in the wine. Citric acid, of course, is an effective iron chelating agent, and a number of chemicals have been used for metal removal, and that's where I'll stop.